Using Raoult's law to calculate the vapor pressure of a component. So Raoult's law is saying that you can use, if you have a solute dissolved in a volatile solvent, the vapor pressure of that volatile solvent is going to be less for the mixture than it would be for the pure solvent. And you can actually calculate that using the vapor pressure of the pure solvent multiplied by its mole fraction in the mixture. So your pressure exerted by the solution as opposed to the pure solvent is going to be your mole fraction of your solvent in the mixture multiplied by your pressure of the pure solvent. So I'll use that little to say the pure solvent, right? We usually use like a little symbol like that. Okay, so we've been given the pressure exerted, the vapor pressure of the pure acetyl bromide. Okay, so the acetyl bromide is our solvent. Okay, and our solute is this chloroform. Okay, so what do we need to calculate mole fraction? Okay, so we've got that the solvent pressure exerted is 45 torrs. So mole fraction, which is X, mole fraction of whatever component is going to be the number of moles of that component, we just call it A, divided by the total number of moles in the whole mixture, in the whole solution. So what we're going to have to do here is calculate the number of moles of our acetyl bromide in, was it 134 grams, and our number of moles of chloroform in 96.7 grams, add them together to get the total number of moles, and then we can calculate our mole fraction of, in this case, our solvent is the acetyl bromide. So I'm going to assume at this point you know how to calculate molar masses, because that's like a Gen Chem 1 thing. In fact, I should probably assume you know how to calculate the number of moles of acetyl bromide in 134 grams, etc. But we're going to go ahead and do it. Okay, so when we calculate the molar mass of acetyl bromide, we should get about 122 grams per mole. I like to teach that we're going to write it out as an equivalency. So 1 mole CH3COBr weighs exactly 122.946 grams instead of using the grams per mole. Why? Because that makes it easier to put into a unit conversion. I'm going to do the same for my chloroform, my solute. So 1 mole of chloroform weighs exactly 119.355 grams. All right, so let's work out the number of moles of our solvent, the acetyl bromide, which is 134 grams. Every 1 mole of acetyl bromide, so much typing, weighs exactly 122.946 grams. So if I stick that in my calculator, and I am going to round this because I can see we're only being asked for 3 significant digits. So 1.0899 moles of acetyl bromide. Okay, let's make that look neat and tidy, tidy and neat. So we can see our grams are cancelling, giving us our number of moles. Okay, so don't stop there. We're not done yet. We've also got to know how many moles of solute we have. So our solute is the chloroform, so 96.7 grams of chloroform. Every 1 mole of chloroform weighs exactly, what did I say, 119.355 grams. Stick that in your calculator, and our number of moles of chloroform in the mixture is 0.8101 moles. Also useful to notice that we can see that the solute is the minor molar component. There are less moles of chloroform than there are of the solvent, the acetyl bromide. All good to know. All right, so then we need to work out our total number of moles in the solution. So that is going to be my number of moles of my acetyl bromide and my number of moles of chloroform added together. So 1.0899 moles plus 0.8101 moles. It's going to give me a total of, drumroll please, 1.9000 moles total. Okay, so then we can do the mole fraction of what we're interested in, which is the acetyl bromide. So we're going to take the number of moles of the acetyl bromide. It takes so long to type. Divide by the total number of moles in the whole shebang. So that was 1.0899 moles of my acetyl bromide. My total number of moles was 1.9000. The moles are going to cancel out. The mole fraction is essentially just unitless. So it's going to be a number between 0 and 1 because it's essentially a decimalized percentage, like a ratio of like a molar ratio of components, if you like. So that comes out to be what, 0.5736. So now I can take that mole ratio and stick it into Raoult's law to calculate the pressure of the solution. Now, a little word about units. Because mole fraction is unitless, then your units for your solution for pressure are going to come out as the same units as the pressure you were given of the pure solvent. So if you have been given the pressure of the pure solvent in torrs, the pressure of your solution is also going to come out in torrs. So in this case, we're being asked for the answer in torrs, so we don't need to do any kind of unit conversion of the pressure. If you do, remember, 1 atmosphere is 760 torrs. We know unit conversions, right? But let's go ahead then. So 0.5736 multiplied by the pressure exerted by the pure solvent, 445 torr. Okay, so mathematically, what we should be expecting is going to be a smaller number than the pressure exerted by the pure solvent. And chemically, that makes sense because we know the presence of solute particles and solute solvent interactions is going to decrease the vapor pressure in the solution versus the pure liquid. And bum, 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 we get an answer of 255 torr. We were asked for 3 significant digits, so that is A-OK.